Hello, I am Chris Carlson. We are the Hash Browns, and this is our final project submission for EAS3800 aerospace measurements.
My name is Nathan Naspich.
Hello, my name is Paresh Chauhan.
Hello, my name is Matthias Tice.
This experiment is used to provide Arduino kits to find the distance using an ultrasonic sensor, temperature using a thermometer, a thermistor, and then water depth using a water depth sensor that we all create using an Arduino board and creating our own code, calibrating, decoding, and eventually trying to find the real values. The requirements for this project were to do lessons 11, 13, 14, and 21 from Arduino to calibrate the temperature measurement system, to calibrate the distance measuring system, the ultrasonic sensor, and then to calibrate the water depth measurement system, and then to assess the resolution of each one, and then try to find the confidence interval and graph them, and try to find what possible errors we have.
Our initial plan to meet the project's requirements was to take each portion of the kit and to test them and slowly calibrate them using some of the code on the Arduino, and to sort of set boundaries for each one of them and sort of try them at each one, and then make sure we get it so that the measurements we were measuring in real time were
Temperature measurement system. You can see you have the LCD display, the Arduino, and the breadboard. On the breadboard, we have the 10 kilo ohm resistor and the thermistor. We have it wired directly as the manufacturer Arduino had it in their circuit diagrams. Here's our code. We had our first void setup, our first area, our main loop, and then our second main section, our loop. In the first one, we did initializing the LCD essentially, and the second one was then taking the temperature and displaying it, making sure to convert to Fahrenheit, Celsius, and Kelvin, and such like that. Some issues we ran into is one side of the thermistor could be heated more than the other, whether that be like a computer fan or just other external things, hitting the sunlight, air conditioning, whatever. That, and when we're cooling it, putting a piece of ice on it, is not a good idea because ice melts water. Water on electronics is never a good idea.
So this diagram shows how we set up our motherboard for the distance sensor. As you can see, we have the 4 wires connecting to the Arduino board. And then here we have the code that shows how it ran. We have the first setup loop, and then we have another loop to tell the distance.
in the wiring diagram for the depth sensor. It's simply just plugged from the red to the positive 5 volts, black to the ground, the green's the data wire. If you move over to the code here, you can see at the top, just sort of naming a couple of the points, and then at the bottom, it's getting the ACT values, or just pulling the values from it and presenting them. And then there's an if statement. This is just basically making sure our values aren't too bright or too far off, and making sure they stay true to something we measured in real life.
The depth thing that we kept having was that if it was already wet when you put it in, it might have screwed up the values, and then for some reason we always got different numbers in the actual real-world depths. About how we calibrated everything. Temperature, we started putting ice on to get cold values. When we got room temperature values, we took the ice off, letting it cool or warm up, and then we did steam, letting that warm up. We let it sit for like 30 seconds to a minute for each one, letting them settle. And then we keep rerunning it until we get the accurate values. Like we got accurate values pretty much every time with that one. On distance, we have to make sure that the plate we're using is perpendicular, otherwise we get wrong values. Luckily, that's the only thing we had to do because we kept getting the correct values every time other than that. And then for the water depth sensor, we just couldn't get that one to accurately read our things no matter how we calibrated it. We had to make sure though that every time we had it wiped off, just be completely dry going back in for each depth though. The big significance of this project is we learned how to build our own devices for our experiment and calibrate and debug and all that. For each one, so we can talk about for the depth sensor, we learned that you definitely need to reset back to 0 every time. So for this one, essentially it's wiping it off, making sure it's absolutely dry before it goes back in, otherwise it would mess it up. Then for the temperature one is to make sure that there's no environmental impacts that are hurting it, such as the computer fan that we were talking about earlier that was heating up one side. And then for the ultrasonic sensor, one thing we have to really remember is to make sure that you are perfectly perpendicular to something like that. So that it is accurately getting the distance. It's just kind of something we'll need to learn in the future, because not necessarily for like an ultrasonic sensor every day in our lives, but to make sure that we follow like the theory of how the thing works and perform the experiment correctly. Otherwise, we'll have to redo it or submit invalid answers. In our lives, our engineering careers, this is all important because it's kind of like a good baseline of like how we should approach an experiment where we are not given the code, we're not given a pre-built system. It's not like all the other labs that we had done. It kind of shows us like what we need to do and what we will be doing in our jobs of building it from scratch to get the results.